Welcome everyone. Today we're going to be looking at the derivative. So we're going to kind of see our first major calculus result that we're going to be looking at. And before we get into it, let's just kind of recall where we left off last time. And what we were talking about at the end of last class is this idea of having a slope formula. So we were looking at this curve y equal to x squared. So just our nice parabola here. And we said, wouldn't it be nice if there was a slope formula, and we said it was just 2 of x. Didn't say how we got that, but I just said the slope formula here was 2x. And the way we could use this slope formula is, or essentially what it allowed us to do, is the slope formula, if we plugged into it, would give us the slope at any point that we want along the curve. So for instance, we looked at a couple points here. We looked at x equals -2. I think we talked about x equals -1. And what we did is we took each of those x values that we were interested in, and we just plugged them into this formula. So for instance, when x was -2, we plugged it into this slope formula, 2x. However we got that formula. And we got 2 times -2, which was -4. And so what that told us is that at this point, the point on the curve at -2, the slope of our graph, or essentially the slope of the tangent line, was -4. And we kind of verified it graphically by drawing in what we thought the tangent line would look like. And yeah, it does look like a slope of -4. All right, so what we're going to see today is, well, how do we actually get this slope formula? How do we go from having a curve of y equals x squared to this slope formula of 2x? And we're going to see that this is going to be our derivative. So this 2x is really going to be derived from this curve x squared. All right, so let's get into it. And so the derivative of a function f of x, the notation that we're going to use is f prime of x. And essentially what this derivative does is it's going to tell us the slope of our curve at any point x. And so the process of actually calculating this derivative, we're going to call differentiation. All right, so let's look at just a little graph for what's going on. So we have our curve at x, or we have our curve y equal to f of x, and then we're interested in a specific point somewhere on that curve, and that point happens at some specific x value. So maybe x equals a. And then at that point, we can figure out what the tangent line is to our curve. And so when we start talking about the derivative and the function, we're going to have two kind of different functions to consider now. And it's going to be helpful to just kind of keep track of what each of these is telling us. So at x equals a, where a is just some specific number, we have our function f of a. If we were to plug into the original function, f of a tells us the height of our curve. At x equals a. So it tells us how high we are above or maybe below the x-axis. And then f prime of a, this new function we're going to be talking about, the derivative, if we plug into that, that's going to tell us the slope of the curve at x equals a. So the original function tells us the height, the derivative tells us the slope. All right, so let's look at a couple specific examples here. Let's look at example 1. And we're going to look at linear equations, graphs of lines. And so for lines, we kind of already know what the slope is. So essentially, we already know what the derivative is. So for instance, in this first one, f of x equal to mx plus b, well, that's just a line. The graph of that function is just y equal to mx plus b. That's just a line. And we know that the slope of that line is m. It's just the m on that mx term. And so what this tells us is because the slope of our line, well, we know what the slope of our curve is. So the slope of our curve at any x value is equal to m. And that's because lines, well, it just has one slope. It doesn't change. And so what this tells us then is really the derivative, if the slope of our curve is m, well, then that means our derivative is also going to be m. Okay, so that we already know how to find the derivative for kind of a nice variety of functions already. All these linear equations, mx plus b, we can find the derivative. It's just the slope, m. And then kind of an even more special case is this other one, f of x equal to b, where b is just a number. Well, the graph of this is just a horizontal line. So this is just another line, y equal mx plus b, with m equal to 0, the slope set equal to 0. And so the graph of a horizontal line is completely flat. And so that means the slope of this curve, so the slope of a horizontal line at any x value is just going to be 0, which means the derivative is going to be 0. So if we have a constant function where our function's equal to just a constant, then the derivative of that is going to be 0. So these are kind of two special cases that come back to the fact that we know what the slope of a line is already. The slope of a y equal mx plus b, m is the slope, and if it's a horizontal line, well, then that slope is 0. So that means our derivative is 0. All right, so let's kind of get to one of our main derivative rules here. And we kind of want to go beyond just lines. So we want to be able to find the derivative for things other than lines. And the one rule that's going to help us with that is this power rule. And what it does is it tells us how to differentiate power functions where f of x is equal to x raised to the power r. So this is a power function, x raised to the power r. And so when we use this power function, this power rule, what it tells us is that the derivative f prime of x is equal to r times x raised to the r minus 1. Now you can just remember the formula here, but I kind of like to think of this as a process. So we're going to start with a power function. And let's see what this rule says. Well, the first kind of important thing to note is that a power function, the variable is kind of on the main level, and our exponent is a constant. So this r value really can be any number. And what this differentiation process, how it works, we're going to differentiate this thing. And I kind of like to think of it in 3 steps. So I'm going to look at this old exponent of r, And to get the derivative, I'm going to bring that old exponent down and put it in front. So that's going to be my first step. I'm going to put that old exponent in front. So we're going to put that in front. Then our second step is going to be, we're going to keep x the same. So whatever variable we have, sometimes we might use something other than x. We might use like t. Whatever variable you have, you keep it the same. So that's our second step. So we're going to keep it nice and the same there. And then the last thing we're going to do is we're going to subtract 1 in the exponent. So we're going to get a new exponent. And that's kind of how power rule works. Kind of this 3-step process. Bring down the old exponent, keep x the same, and then subtract 1 in the exponent. And you have your derivative. So let's try this out. Let's see how this process works. So in example 2, we have a bunch of power functions here, and we're going to calculate their derivatives. So let's start with f of x equal to x squared. Let's calculate that derivative. All right, so here our exponent is 2. Well, when we go on and we want to calculate the derivative, this is just a power function. So we're going to take this old exponent, we're going to bring it down, put it in front. So the 2 is going to go in front. Then our variable is going to stay the same, so it's going to stay as x. And then we're going to subtract 1 from the exponent. And then if we clean that up, we're going to have 2 times x raised to the power 1. And then normally we don't write that exponent of 1, so it's just 2x. And so this was kind of where we left off from last time. This was the curve we were looking at, the parabola x squared, and we said that 2x was the slope formula. We didn't say where that slope formula came from. We just said it was it. And now we're seeing that it's coming from this derivative process, that this slope formula of 2x is really coming from this power rule. All right, let's try another one. So let's look at x cubed. Let's try this x cubed. Let's differentiate this. And so in this case, the exponent is 3. So we're going to calculate the derivative. We're going to get f prime of x. So same process. We're going to take that old exponent. We're going to bring it down, put it in front. So we're going to have a 3 there. We're going to keep x the same. And then we're going to subtract 1 in the exponent. So we're going to get 3 minus 1 up there. And then if we clean that up, we're going to get 3x squared. Now when you're doing these, I'm kind of showing probably more steps than we really need to. So in this first one, once you get the hang of these, you're probably not going to show kind of these middle steps. Same thing for right here. You're probably not going to show this step. So I'm only showing this just because, we're just getting into it. So, as you practice these, you might start off by showing these steps. But once you have the hang of it, you're probably going to go right from the function right to its derivative for the power rule. Now, ones that you might have to do a little bit extra are kind of these last two. So if we have square root x, this one is actually going to take a little bit of, not too much, but a little bit of work. And that's because right now, it's not really written as a power function. It's written as a root function. And so a common strategy that we're going to use is to rewrite any root functions that we see. So if we have the nth root of something, we're going to rewrite it as a power function. So the nth root would become raised to the power 1 over n. And so in our case here, we have the square root function. So normally for root function, there's a little number in front here. But for square root functions, that's the most commonly used one. Square root functions could have a little 2, but we normally leave that off. It's normally understood. So other examples would be like the cube root. There would be a little 3 in front, or a fourth root. There would be a little 4 in front of our root sign, and then we would convert those either to raised to the 1 over 3 or raised to the 1 over 4, things like that. But in our case here, we're going to rewrite this as x raised to the 1/2 power, because we're dealing with the square root. And so when we go on and calculate the derivative, what are we going to do? We're going to take this old exponent, we're going to bring it down, put it in front. So we're going to have a 1/2 in front. Then we're going to keep x the same. And then we're going to subtract 1 from the exponent. And if we clean that up, we're going to get 1/2 x raised to the negative 1/2. And same deal. I'm not going to expect you to show this step in the middle, but it certainly doesn't hurt, especially when you have these kind of fractional exponents. It can get a little tricky trying to do too much in one step. So I definitely don't mind here if you want to show this. And just for a little practice, how did we go? How did we go from this exponent to the negative 1/2? So in case you don't see it right away, 1/2 minus 1, if we get a common denominator between these two terms, we could rewrite that 1 as 2 over 2. And then when we have two fractions and we're either adding or subtracting, we can just add or subtract the numerators. So we'd get 1 minus 2 over 2, which ends up being our negative 1 over 2. Okay. So one more. Let's look at this function 1 over x. Let's see how to differentiate this. And this is another one where it's not really written as a power function yet. This is a quotient. So our first step, and this is going to be a kind of a recurring strategy that we come back to over and over, is to rewrite this fraction with a negative exponent. All right, so, normally with these fractions, there's going to be an exponent on the x. Now here there is one, it's just not usually written, so the exponent is 1. And the way we do this, using negative exponents, is we write down we take the term from the denominator, and we just write it as is. So it'll be x raised to the negative, or x raised to the 1. And then getting rid of the fraction, what we're going to do is just make whatever exponent we have there, we're going to make it negative. So in this case, 1 over x gets rewritten as x raised to the minus 1. And now this is a power function, so now we can use our power rule. So the derivative, what are we going to do? We're going to bring this negative 1 down, put it in front. We're going to keep x the same, and then we're going to subtract 1 from the exponent, which is going to take us from negative 1 down to negative 2. And so here, I kind of eliminated that middle step, so I just kind of wrote what the derivative was. So once you get the hang of these, that's probably what you'll be doing. Perfectly fine. Now we could, sometimes it is helpful to rewrite a negative exponent back as a fraction. So sometimes it's going to be helpful to put this back. And what we would get in that case is negative 1 times 1 over x squared. So if we put it back as a fraction, the we get rid of the negative in the exponent, and then it just becomes a fraction, so 1 over x squared. Or if we wanted to go a little bit further, we could write this as negative 1 over x squared, like that. But perfectly fine if we wanted to just stop here. So for now, we could just stop with this. All right, so that's going to do it for today. And what we're going to see in class tomorrow is, or our next class rather, is how we can actually use this derivative to help us find the slope of some curves, and then maybe even the equation of our tangent line at some points. So we'll see you then. Bye-bye.